Welcome. You're watching Nanotech today. I'm Dr. Ogan Gorel, your host. Our guest is Professor Franz Geiger. I'll introduce him shortly. He's at Northwestern University, and our topic for today on Nanotech today is making, quote, sense of DNA.
Hi, Ogan.
Professor Geiger, pleasure to have you.
Pleasure to be.
In fact, since Nanotech today and nanotechnology is truly global, I should say to our German friends, willkommen.
Willkommen.
And at a very high level, what is this research is about, and then we'll dive into the details.
Absolutely. Well, we have at Northwestern the first federally funded nanoscale science and engineering center. This is a center that's driven by the NSF. It's a multi-million-dollar center. It's got about 30, 40 faculty involved. And the idea, really, the premise is to come up with very basic fundamental chemistry experiments and engineering experiments to develop a chip that allows you to do point-of-care detection of diseases that are currently very difficult to determine and to assess. Some of these are involving Alzheimer's. We're working with a number of people from the medical school using, for instance, small molecules, adults that are linked to indicating Alzheimer's. Everyone has them at very small concentrations, and Alzheimer patients start to develop them at higher concentrations. Right now, the only diagnosis for Alzheimer's is post-mortem. You have to cut into the brain to see what's going on.
Or a biopsy.
Exactly.
Basically never done.
Right. And it would be fantastic to, of course, start tracking these diseases now at an early stage. And so disease tracking and diagnosis will then, of course, lead to improved chances of prognosing and then finally curing. The device we're building at Northwestern is literally handheld. And it has a variety of basic physical chemistry and biochemistry involved in it. And the fundamental aspects of it were developed by Chad Merkin, who is the director of the NSEC at Northwestern. The idea really is to look at the interaction between DNA on a surface or in solution with target molecules. This might be complementary DNA, this might be a biomarker, it might be small molecules, or even inorganic cations and anions.
And that's where the sense anti-sense comes in, because
Absolutely.
Your experiments involve combinations, or I should say at some point single-stranded DNA, and then also the anti-sense testing DNA, if you will.
Exactly.
Complementary strand.
Exactly. Sure.
Well, and you have a model here.
Yeah, we brought a model. This is one of these structures.
Right here.
Yep.
And so, obviously, most people know the structure, but if you can highlight the components of the DNA that are relative to your research.
Basic idea is you've got on the yellow side, on the outside, phosphate groups. These are charged, of course. They're linked to sugars, and then each sugar is linked to a base. And so those are the three components. You then have the interaction between a single strand going up your spiral staircase, if you want, and a complementary strand, which is now wrapped around it, and that forms, of course, a duplex through hydrogen bonding interactions in the center. This is exactly the model that we bought and built, in fact, with our students. It was a great learning experience of a thymine 15-mer strand, complementary to its adenine 15-mer strand. So we're looking at TA 15 mers, 30 mers, etc. This is because it's a good test sequence that allows us to apply our spectroscopies in two ways. We probe, without having to use labels, the charges on the DNA strand. So when you look at the interaction of this molecule, let's say a single strand, or even a duplex that's formed when it can interact as a sequence, for example, as in the form of a G quadruplex, where it can now interact with even cations, let's say mercury or potassium. The interactions are primarily driven by electrostatic and Coulombic interactions and hydrophobic interactions, non-covalent interactions.
Yes.
And because there's so many of them, the total energy, of course, involved is quite strong, and that's why the molecules stay together. If you want to have access to that information in terms of thermodynamics, in terms of structure and spectroscopy, many times people use labels, and labels are extremely powerful for deriving this information, but ultimately those experiments tell you, in terms of a fundamental aspect of the interactions, what the label is seeing. It would be nice to take a look at the molecule itself and study the molecule without having to modify it, first of all, with labels, and second of all, without having to use labels to study it,
I mean,
that are extrinsic.
Yeah, extrinsic labels. Someone would say the native molecule.
Exactly, the native molecule. Now, we use labeling all the time in terms of fluorescent labeling, etc., because it's a very powerful technique to detect extremely small quantities of DNA on a surface, for instance. In our spectroscopies, which are nonlinear optical spectroscopies, we can detect about 1,000 molecules on a surface in our laser spot. We can look at the phosphate negative charge. We can count how many charges there are. They light up like a Christmas tree, so this is effectively an intrinsic label that is part of the molecule.
Native to the molecule.
Native to the molecule, that's right. And we can also look at the CH stretching region in the infrared and ask questions regarding supramolecular orientation and chirality. So we can do circular dichroism spectroscopy, not with having to use millimolar amounts, which right now is necessary for protein structure determinations using CD.
We're coming right up to a break.
Yep.
I think it's important to emphasize you're using the native molecule because a lot of, and thymidine, adenine sort of precursors, because in the clinical applications you want to use any molecule.
That's exactly right.
Without having to extrinsically label it.
Correct.
Stay right there. We'll be right back. Some more about making sense of DNA. Welcome back. We're here with Professor Franz Geiger, Associate Professor at Northwestern University and Dow Chemical Company Professor. We're talking about DNA chemistry, its relation, the surface chemistry thereof, and the very unique spectroscopic experiments, all in the context of being able to manipulate and analyze native, non-intrinsically labeled, non-extrinsically labeled DNA, which obviously, as you said at the outset, has tremendous clinical applications.
Absolutely.
But we're looking at the basic science. So let's look a little bit about the chemistry. I understand you have a picture for us to describe.
Yeah, that's correct. So there's a picture here that shows how you can covalently link DNA to a silica or any other oxide surface. These are interesting oxide surfaces because they're transparent, for example, either to the infrared if you use silicon or to the visible for optical probes. We've developed this N-hydroxy-succinimide ester. The hydroxy group and the succinimide linker is a very good leaving group. It's replaced by incoming amine-terminated DNA single strands to form an amide group. And of course that amide group is what keeps your proteins together, so it's a very stable chemical bond.
It's also basically organic, if you will.
Absolutely.
It's not only a native DNA, but you're talking about not very exotic chemistry.
Not very exotic chemistry, and what you've now accomplished essentially the immobilization of the DNA on your surface, which is very important when you think about sensory development, where you want to be surface-based in most cases. And then in pink we show the interaction now of the incoming complementary strand that now forms the duplex or the hybridized compound. We can determine then these interactions directly without, again, having to use labels and address questions regarding structure.
Sure. Well, I think the implications of the amide linkage are also interesting. Not only does it imply not so exotic chemistry, not that we're against exotic things, but when it comes to clinically relevant sensors, you want basic organic chemistry, if you will. But the other implication is, just as the properties of the peptide bond in proteins, there's an element of rigidity and strength, partial double bond character and so forth, but also flexibility.
Absolutely.
So that you can indeed have a single strand. Just for our audience, and I really appreciate your time.
Well, thank you so much for having me.
And we're going to look forward to hearing more.
Absolutely. Thank you.
Thanks a lot.
Thank you.
You're watching Nanotech Today.